Today we're going to learn about something called a one-sided limit. And basically what we're going to do is we're going to take a problem we already know how to do and split it in half. Because we learned how to do limits from both sides, and a one-sided limit is just a way of me asking you to do half of that question, only do one side of the limit. So here's kind of what I was saying a minute ago or a second ago. I said we learned earlier that every limit is actually two questions. You got to ask what happens coming from the left and what happens coming from the right. And a one-sided limit is a way for me to ask you those questions one at a time. So what we want to focus on first is the notation. So this right here is a one-sided limit, and the difference between this and the limits we've been doing, it's very tiny, it's that little plus right there. So if you look very, very carefully on the A, you have that little plus right there. It's in the exponent spot. It looks like a to the plus power, even though that doesn't really make sense. Well, that little plus means it's a one-sided limit, and I'm only asking you to check on the right side, or where numbers are a tiny bit bigger. That's another way to think of it. So basically, if we're doing x approaches 3 from the right side, if you're doing it from a graph, I mean, it's literally, that's what it's asking, is coming from the right side. Now, if you're doing it more numerically, it means numbers a tiny, tiny bit bigger than 3. And that's what the plus means. It basically means x approaches whatever number, I'll say 3 again, plus a tiny, tiny bit. Really close to 3, but a little bit bigger. Then you guys can probably guess, if I put a minus there, it means from the left. So again, just like last time, the only difference is we have this little teeny tiny minus right there. Again, it's the exponent spot. It looks like a to the minus power. And that means we're looking for numbers that are just a tiny, tiny bit smaller than a. So again, visually from a graph, it means we're coming in from the left side. Numerically, it means you have numbers a tiny bit smaller. So if it was the limit as x approaches 3 from the left, you're looking at 2.99999. Real close, but a tiny bit less than 3. So here's how it works. You know how to do all of this. We're just taking a question you already know and splitting it in half. So here is the limit. No plus, no minus. This is what we've been doing before today. The limit as x approaches a of f of x. Now we're going to say it only exists if the limit as x approaches a from the right of f of x equals the limit as x approaches a from the left of f of x. And that's exactly what I told you on our graphing day. I'm just using our new notation to say it. So you already knew this. This isn't new to you guys. It's just a new way of saying it. Now, if they're not equal, the limit does not exist. And we say DNE. So I'm going to show you an example very similar to one we've looked at. Let's take a look at a piecewise function. And let's say I'm doing the limit as x approaches, I think I used 3 in the notes. So let's say on one side the graph goes up here to this point, and we'll make that 3, 2. And on the other side it goes down here to that hole, and we'll call that one 3, -3. So basically, from what we learned earlier, from the left, it's going here. From the right, it's going here. So the answer to the limit question is DNE, does not exist. We already knew that. But see, now I can ask you to answer each question separately. If I ask you, what is the limit as x approaches a with the little plus on it? That means starting from the right. That's the green one. So the answer to this question is -3. And if I asked you, what is the limit as x approaches a from the left with a minus, that's the red one. That answer would be 2. So those questions, the answer is not DNE. Those ones do have an answer. And more importantly, because their answers are different numbers, that's why the original limit does not exist. So you can always check left and right limits separately. If you get the same answer for both of them, that's also the answer for the limit question. If you get different answers for those, then the limit question does not exist, it has no answer. All right, so for this example, we are going to draw our own graph, f of x, and we're going to make all 5 of these things true. Now, as you look at it, I want you to think of it kind of as 2 groups of questions, because these 3 things here tell me what happens right around where x equals 2. The bottom one tells me what happens when x is 2. The top one tells me to the left of 2. And the middle one tells me to the right of 2. That's what the notation means. Now, the bottom 2 questions do the same thing, but tell me what happens around where x is 4. So let's do this. I'm going to put in a red line to match my notes to the left there at 2. And I'm going to put a purple line to match my notes here at 4. And let's do a graph that makes all 5 of those things happen. Now let's start with the easy ones. F of 2 equals 0. That is a point. I'm going to put a point right there at 2, 0. That's done. So check, that one is done. Now f of 4 is undefined. That means no matter what happens, when I'm done with my graph, I should have no points on that purple line. I shouldn't have a graph that crosses over it. That counts as a point. If it crosses over, there has to be a hole, an open circle. But when I'm done, there should be absolutely no points on that purple line. I won't check it off until I'm done with the question. Okay, now let's do the limits. Let's start with the 2. The limit from the left with the minus is -3. So what I'm going to do, I'm going to put an open circle here at -3. You can't have 2 points on the line. We already decided the point is at 0. So if I want something on that line, from now on it has to be an open circle. And I'm going to say, my graph, you can draw anything you want, as long as it goes to that point right there. You have anything what you want as long as it's going right to that open circle at -3. So that one's done. Now the middle one says the limit from the right at 2 goes to 0. Well, that's where the point is. So basically, I'm going to be approaching that point right there. And I'm just going to draw a little tiny little line for now because I don't know where it goes. I got to figure out where it goes on the purple one. All right, so I'm done with the 2's. Let's figure out the 4's. So I already decided it's undefined. I can't have a point on that line, but I said the limit as x approaches 4 with no plus or minus equals 5. That means both the plus and minus equal 5. Remember, if I say the limit as x approaches 4 is 5, that means it's meeting at 5 from both sides. So when x equals 4, the first thing I'm going to do is go up to 5 and I'm going to put an open circle. Remember, it has to be an open circle because f of 4 is undefined. We can't have a point on that line. And it needs to approach that line from both sides. So what I'm going to do is, where I left off on the red one, I'm going to go up here to that open circle, and then I'm going to continue right through it, and just basically do anything I want there. And now I can check off that one, because the limit is 5. It's meeting at that point that's up 5 on both sides. And I can double check. I have no points on my purple line, so I can check off that one. And right there you have a graph that shows exactly what I asked you to do, all 5 things. Now the important parts of the graph are what you see right here. You should have the open circle approaching from the left. Up here you should have a closed circle approaching from the right. And right here you should have an open circle basically approaching from both sides or crossing right through it. None of the rest of it matters. Like if you drew a different graph with like what's happening with the red graph off to the left there than I drew, that's fine, because that has nothing to do with the limits I talked about. Or if you did something with the other end, the purple graph off to the right side, again, it's fine. The 3 parts that I circled in yellow are the real important parts of that question. Okay, so here's our next example. My question is, if the limit as x approaches 2 from the right with the plus is 5, and the limit as x approaches 2 from the left of the same function, f of x, is 0. So we have something like this. We have one of those piecewise functions. They're going to different places. Can f of 2 equal a completely different number, 3? Can it be something completely different than the 5 and the 0? If so, what would the graph look like? Okay, let's see if I can squeeze it in here even though it's behind me. So we're doing the limit as x approaches 2. I think we can because it's all positive numbers. So I'm going to draw in this line right here at positive 2. And I'm going to say the limit from the right is 5. So I'm going to put an open circle at 5, and I'm going to draw anything I want going towards it from the right. Now the limit from the left is 0, so I'm going to put an open circle there also, and again, draw anything you want over here as long as it's going to that point. Now notice I didn't fill in either of those points. I put open circles on both of them. And the reason I did that is because it told me f of 2 is 3. So the point's going to be one of those floating points like we saw earlier. So the answer to the question is yes, you can. And the graph would look something like this. You would have that point kind of floating there on 3, and then you would have one limit coming in up here at 5, and another limit from the other side coming in down here at 0, but you have to have open circles on both of them. You can't have more than one point on that vertical line. Okay, here's our last example for today. We're going to do it in parts. So we have a piecewise function. F of x equals, and you have a piecewise function, you can see it. And the first thing I ask you to do is find the limit as x approaches 4 with the little minus. Now we're actually going to do this using our analytic trick. We're going to use direct substitution, which means I want to plug in 4 for x. And we're going to forget about the minus. If you're doing direct substitution, it doesn't matter if you have a plus or minus as far as the plugging in. The plus or minus tells you where to plug it in. So remember, the minus means a little tiny bit less. So what I'm looking at, I'm not really looking at the number 4. Remember, I'm looking at like 3.9999999, something just a tiny bit less. But it is less. And that tells me to use the equation on top because that's the less than 4. If x is less than 4, which it is, it's only a tiny bit, but it is less than 4, I'm using the top equation. So I'm going to do direct substitution. I'm just going to plug 4 into that equation. I'm going to have 2 times 4 plus 7. That would be 8 plus 7 is 15. And that's the answer to the question. Direct substitution worked. I plugged in 4 and it worked. So let's do the limit from the right. And again, I want to do direct substitution. I want to plug that 4 in. Now remember, the plus means we're taking a look at a number that's a tiny bit bigger than 4. It's like 4.00000001. Well, even though it's only a tiny bit, it is greater than 4. So that tells me this time I'm plugging it in here. So I'm going to plug in 4. Forget about the plus when you're plugging in. I'm going to plug it in, and I get 4 squared, which would be 16. So my last question for you is, what is the limit as x approaches 4 of f of x, period? Now you don't need to do extra work for this. All you're doing is you're checking the 2 you've already done, whether they're the same. And they're not. I got 15 for one and 16 for the other. So this answer is D and E, does not exist. They were very close. If we had gotten, like if they had both come out to 15, then the answer would be 15. Or if they both came out to 16, the answer is 16. But if you get different numbers, then the limit does not exist. And the reason I made it so they came out so close together, 15 and 16, if you were trying to do it by graphing, it would be very hard to tell that they didn't meet at the same point. If one of them's coming in here to 16 and one of them's coming in here to 15 and you're drawing it by hand, it might look like they're meeting, and you might think that you do have an answer there. But by plugging in values, by basically plugging 4 into each equation and seeing if you get the same number, that's a good way to tell whether or not the limit does exist. And just remember, the less than is the limit from the left, and the greater than is the limit from the right. All right, you guys get started on the assignment, and I will check for questions tomorrow.